Here's our project, infrared vibration sensitive LED drum and metronome, also known as LUDS. So our group consists of four people: Aaron Holloway, Ajay Natanmay, and Elisha Piraman, all of us electrical engineers, and Malcolm Donaldson, who is photonic science engineering. So to begin with our project description, it's a simple drum with six reflectance sensors under the skin, which detects the vibration during each beat, and it outputs a visual signal to the LED strip inside the drum and to the LCD display. It has two modes: metronome uh, and sensing. In metronome mode, it acts as a musical metronome that flashes the LED with a specific metronome set. Uh, and in sensing mode, it detects during each bit and it outputs to the LED strip.
Here are our goals. Our key goal, which was the most important to hit, was the LUDs needed to be able to detect the vibration of each strike, and the rest of our core goals are listed below. Our three key engineering specifications that we had to meet are that the LUDs should allow for a maximum of 240 LED flashes per minute in metronome mode, which we successfully achieved. That the reflectance sensors must be placed between 0.25 and 3 millimeters below the skin of the drum to detect vibrations that from any point in the drum while not detecting the skin while the drum was at rest. We managed to find that the best distance for the sensors was between half a millimeter and 1 millimeter. And our last specification that was that we needed to have both a AC adapter and a rechargeable battery, which could operate for a minimum of 2 hours, which we also achieved.
Here we have our project block diagram. To the right is the legend that helps indicate which teammates' components that they worked on.
Here we have the layout of the project and how it will be placed inside the drum. This figure is looking down into the drum from the bottom. The green line shows where the LED strip will be placed on the inside of the drum using adhesive glue, and the red area indicates where the sensor array will be placed.
One of our key components was the sensors, since they're what allowed the drum to interact with the LUDs, essentially. For this sensor, we went with QRE1113s from Onsen. They're analog sensors that can capture varying light levels. They have a short effective range and were both cost and power efficient. A small diagram of how these reflectance sensors work can be seen on the right side of the screen.
Here's our MCU selection, which is the MSP430FR6989. It can be programmable in C language. Since we have one switch, one knob, which each require two pins to be connected to the MCU, and we also have the LED strip, which needs one strip to be connected to the MCU for the output and a ground pin. And the interior sensors under the skin of the drum requires each one pin separately to send the output signal to the MCU, and we chose this MSP for to connect each of these pins.
Here we have the EagleCAD schematic for the non-inverting op amp. This op amp sits between the MCU and the LED strip.
Here we have the voltage regulator schematic from Eagle that is in between the two voltage source signals and outputs a 3.3 volt signal. Next here is the voltage inverter circuit that takes the output from the voltage regulator circuit and outputs a negative 12 volts to the op amp design circuit.
This is the schematic for the switch circuit that connects to the MCU. These resistors are pull-down resistors to help reduce noise. Similarly, this is the schematic for the rotary encoder and their filters. It has both pull-up, pull-down resistors and capacitors to filter out any unnecessary noise.
Okay, so here's this software design which includes the schematic of the MCU and the output voltage of 3.3 volts will be provided to each of the components. As you can see on the right side of the screen, the pins connected will be initialized to each of the pins that are shown here.
Okay. Uh,
And here we have the PCB layout, specifically the Eagle bread or the Eagle board schematic. There was a complication with the PCB vendor. We got the PCB back, however, it was not assembled. Also, we were dealing with a lack of lead times for many of our components. However, we do plan to solder the PCB in the future.
Here is a demonstration of the LUDS in performance. So it demonstrates how the switching between power supplies works. And here is the LUDS reacting to the beat of the drum. You can see the LEDs are fairly responsive. Here's the LEDs changing colors. Here is the LEDs changing color again, and you can notice an effect where the LEDs flash multiple colors. This was not an initial part of the design, but since this is a performance piece and it looked visually striking, we decided to leave it in. And here's just a continued demonstration of the LUD's sensitivity and dynamism.
Here we have a short demonstration of the metronome part. Here we press the switch to turn it into
Also, here's our presentation of the display. It can be changed from sensing to metronome mode, and back again to metronome and back to sensing, which is shown in the first line. And in the second line, it shows the BPM, which is also changeable using the knob. It can be changed up to maximum of 240, and it can be reduced back to a minimum of 15. So here's our future plans. We complete the final presentation on April 16, and the final documentation will be completed by April 25th. And as soon as our PCB arrives, we will plan on completing the soldering and adding the components to it very soon. And we will complete the other extra features after the course completion.
And this has been the LUDS. We have been Group 10. Thank you for watching.